Today's lecture is lecture 13, which is a continuation of lecture 12, wherein we discussed or rather introduced the concepts of moment of inertia and product of inertia. These two concepts are very important for mechanics, particularly in dynamics problems, and during that lecture itself we set up a correspondence between moments of inertia and the second moment of area, and similarly for products of inertia there was a correspondence with the product of area. Let us start with today's lecture now. Today we will study the effect of coordinate translation on the moments and products of inertia of a body. Translation means the coordinates are moved without rotation. For example, if I consider an arbitrary body shown here, and there are two coordinate systems, Cartesian coordinate system shown. One is this dashed one, center is C, which is the center of mass of the body. So, this coordinate system with origin at the center of mass is x dash, y dash, z dash, and there is an arbitrary coordinate system with origin at O and the coordinates axes as x axis, y axis and z axis. Now, the special feature about these two coordinates systems is that the x axis is parallel to x dash axis, y axis is parallel to y dash axis and z axis is parallel to z dash axis. That is, the axes have been shifted in a parallel manner. There is no rotation involved in shifting the axis. So, when you have let us say the moments of inertia given in the C x dash, y dash, z dash coordinate system, and you want to find out the moment of inertia in the second coordinate system, that is origin at O and x, y, z coordinate system, then what is the correspondence between the, let us say, Ixx and Ixx dash and other quantities? How to set up a relationship so that I can get the moments of inertia in the new coordinate system in terms of the old coordinate system. Same thing for the products of inertia. So, let us see how we can do this. Let us say that again referring back to the same figure, I will consider a small element of the given body. This element has dimensions dx, dy, dz. It is a very infinitesimal element, and the center of this element has a position vector with respect to the old coordinate system, that is the coordinate system at center C. So, from center C to the center of the element, the position vector is r dash. Similarly, the same element is located at a position vector r from the origin of the new coordinate system O x y z. So, the distance between the two origins O and C is given by the position vector rho dash rho. So, it is very easily checked that the position vector r is equal to rho vector plus r dash vector. Now, this rho vector in the coordinate system at O, that is the new coordinate system with the unit vectors as I, j and k. The position vector of the center of mass is xci plus ycj plus zck. So, that the coordinates of the center of mass in the new coordinate system are xc, yc, zc. So, substituting for rho from here, we can easily check that the x coordinate in the new coordinate system is equal to the x coordinate of the center of mass plus the coordinate in the old coordinate system, that is x is equal to xc plus x dash, y is equal to yc plus y dash, z is equal to zc plus z dash. Now consider one of the moments of inertia, that is Izz. By definition, this is in the new coordinate system. Izz is equal to the volume integral of x square plus y square into the material density, mass density rho, taken the integral over the entire volume. Now substituting for x square plus and y square, we will have from this equation xc plus x dash whole square plus yc plus y dash whole square rho dV integrated over the entire volume. And now we expand the squared brackets. So we will, by rearranging the terms, we can easily verify that the previous integral will be now equal to the sum of these integrals. One is the volume integral of xc square plus yc square into rho dV plus twice, these are the coupling terms, x dash into xc rho dV in volume integral, twice y dash into yc rho dV volume integral, and then volume integral of y dash square plus x dash square rho dV. Now xc and yc, the coordinates of the center of mass, they are constant quantity, they are just fixed numbers. So I can take it outside, and inside we will be left with the rho dV volume integral, which is nothing but the total mass of the body. So the first term of this expansion becomes mass into xc square plus yc square, and the last term, which is by definition the moment of inertia around the z axis, z dash axis in the old coordinate system, that is c x dash y dash z dash, the dotted coordinate system. So first and the fourth terms are taken care of, and these two coupling terms, now again xc and yc are taken out as constants. So twice xc into volume integral of x dash rho dV and plus twice yc volume integral of y dash rho dV. Now by definition, these are the coordinates of the, this is the x coordinate of the center of mass in the old coordinate system, that is c x dash y dash z dash, and this is the y coordinate of the center of mass in the old coordinate system. But the old coordinate system, as you can easily see from the figure, is itself located at the center of mass. So in the x dash y dash z dash coordinate system, the coordinates of the center of mass are 0 0 0. So it means that this term and this term are zeros, these volume integral, and they reduce to 0, and hence the contribution is 0, and I am left with Izz is equal to mxc square plus yc square plus Izz dash z dash. So look here, so I have Izz is equal to this expression. Now to understand the first term, this is the mass of the body, and xc square plus yc square, this is the distance between these the square of the distance, normal distance between the z axis and z dash axis. Again refer back to the figure. So this is the z axis and this is the z dash axis. So the normal distance between the two squared. So d square, the normal distance between z and z dash axis, is equal to xc square plus yc square. This is by Pythagoras theorem. Okay. So it means we have a very compact expression, that is the z moment of inertia Izz is equal to, in the new coordinate system, that is located, the origin is at an arbitrary point O, is equal to the old coordinates, the moment of inertia about z dash axis in the old coordinate system with origin at the center of mass of the body plus the total mass into the normal distance between the z and z dash axis squared. Okay. Similar expressions can be obtained for Ixx and Iyy. So, the that is, for example, Ixx will be equal to Ix dash plus x dash plus mass times the normal distance square between the x axis and the x dash axis. Okay. So, this is how we get the correlation, and then we can now turn our attention to the product of inertia, that is Ixy, Iyz, Ixz. The procedure is exactly identical, that is, you write down the expression in the new coordinate system and then expand the terms, that is, for example, in Ixy expression you will have x and y terms which can be written as xc plus x dash. Similarly, y will be written as yc plus y dash. Again, take the product, there will be 4 terms and so on and so forth, exactly proceeding in the same lines. You will have, for example, for Ixy is equal to Ix dash y dash plus the total mass of the body into the product of x coordinate of the center of mass times the y coordinate of the center of mass, as seen by the OXYZ coordinate system. Okay. So, you have to be careful in product of inertia terms, that is, you have to check whether the center of mass lies in the first quadrant or the second quadrant, third or fourth quadrant. So, properly the positive or negative sign of the coordinates of the center of mass, that is xc and yc and zc, should be taken care of, because in the moment of inertia terms the terms are squared, the distance is squared. So, whether negative or positive does not make any difference, because when it is squared it is positive. But in the product of inertia terms you will have xc and yc. So, if xc is negative, for example, then this term will become negative. If both xc and yc are negative, of course, then it will be positive. So, one has to be careful in properly accounting for the coordinates of the center of mass. This whole exercise is called the parallel axis theorem. Okay. Now, let us try to apply this parallel axis theorem with the help of a simple problem. Let me show the diagram and then I will come back to the problem. Here is a rectangular block. Okay. The outside dimensions are 10 centimeter, 8 centimeter and height is 9 centimeter. In the center of this block there is a cylindrical cavity from end to end. So, this dotted magenta color dotted figure is the cavity. So, the net body is a block minus the cavity. All right. So, we have been asked to find out the moment of inertia about a coordinate system whose origin is at the center of this face, this right hand face, whose dimensions are 8 centimeter and height is 9 centimeter. So, A is the center of this face and there is a coordinate system x, y, z located at that point A, and we have to find out Ixx, Iyy, Izz and similarly the product of inertia term. So, go back to the problem. A block having a uniform density of 5 grams per centimeter cube has a hole of diameter 4 centimeter drilled as shown. So, we have already seen. Determine Ixx, Iyy and Izz about xyz respectively having the origin at the center of the right face of the block. Okay. So, I have already mentioned that the net body is the total rectangular cubic body minus the cylindrical cavity. So, we can find out these moments of inertia and then by parallel axis theorem shift it to the new coordinate system whose origin is at A, the center of the right hand face. All right. Well, for rectangular bodies, for cylindrical bodies, spherical bodies, etc., the expressions for the moments of inertia are available in many books, handbooks, in mechanics books, etc. So, we will not derive those expressions from the beginning because that will take a lot of time. You can refer to those handbooks or tables and let us see how we can do this. Now, let us have a coordinate system at the center of mass of the body. Now, where is the center of mass of this body? The outside rectangular block, the center of mass is at the midpoint of the 3 dimensions, that is its location will be at 4 centimeter along this dimension, 5 centimeter along this, and similarly half of 9, that is 4.5 is the height, and the cylinder is also located at the same point. So, the center of mass of the cylinder and the rectangular block, they are coinciding, and hence of the net block, that is rectangular block, solid rectangular block minus the cavity, that will be also at the same location. So, O is the center of mass of the net body, okay, whose dimensions along, let us say length is 5 centimeter, along width is 4 centimeter, along height is 4.5 centimeter. So, at that point we have a coordinate system x dash, y dash and z dash parallel to the 3 edges of the block. Now, for I x dash, what you do is mass of the block divided by 12, this is for the cylindrical body, the solid rectangular block, into the 2 dimensions perpendicular to the x dash axis, that is 10 centimeter square plus 9 centimeter square. Okay. Similarly, I y dash, total mass divided by 12 into the 2 dimensions perpendicular to y dash axis, that is 9 square and 8 square, and similarly I z z, okay, z dash. So, the 3 moments of inertia in the x dash, y dash, z dash axis are obtained. Now, mass, total mass of the solid prism, you can see is 10 into 9 into 8, this is the volume. Now, this is 5 grams per centimeter cube is the mass density. So, it comes out with 3600, and when I substitute in these 3 expressions and simplify these brackets, I will get I x dash is 54,300 grams centimeter square. These are the units of the moments of inertia. I y dash is 43,500 grams centimeter square, and I z dash is 49,200 grams centimeter square. So, I have got for the solid block these 3 values, and if I subtract from there the corresponding values for the cylindrical cavity. So, I will have the moment of inertia terms for the net block. So, for the circular cylinder, again from the handbook or from the tables, we will have mass of this cylinder, that is if the cavity had not been there, that cylinder. So, 1 by 12 of that into 3 r square plus h square. Now, since x axis and y axis are along the perpendicular diameters of the cylinder. So it means Ix dash x dash is equal to Iy dash y dash for this cylindrical body. Okay. So when I substitute over here, everything is known, radius is known, 4 centimeter is the radius, and height is known, namely the height is 9 centimeter, height of the block. So after simplification, I will get it 44382.52 grams per centimeter, grams centimeter square. And for the for the moment of inertia about the z axis, I will have 1 by 2 mr square from the tables. So m is already obtained from here, pi r square is the area into height into rho is m. So you calculate it out, it will be 1113.97. So the net values for the net block, that is the solid rectangular block minus the cylindrical cavity, these are the three values: Ix dash, Yx dash, Y dash, Y dash, Z dash, Z dash, and the net mass of the block is 3034.513 grams. Okay. Now we are ready to apply the parallel axis theorem. Now let us go back to the figure. Suppose I consider x dash axis and x axis. These are two parallel axes. The distance between the two axes, the normal distance between the two axes can be obtained. This is half this dimension. All right. So it means Ixx will be equal to Ix dash x dash plus mass times d square, distance between the two axes, normal distance between the two axes squared. So similarly for y dash y, well fortunately y dash and y axis, they lie on the same line. So there is no need to have parallel axis theorem. There is, that is the normal distance between y dash and y is 0. So it means second term contributes 0, and then for the third z dash, you can again find out the normal distance. So let us see. Sorry. Ixx about A, that is on the right hand face, is equal to about the center plus md square. So this 5 square. So it will come out to be this value. Iyy, since they lie along the same axis, so this distance is 0. So we don't have to do any change. And similarly zz axis, again d is 5 centimeter. So d square is 25. So this is how step by step you get the values, right. Now let us go to another aspect of moment of inertia. In the previous case, the two axes x y z and x dash y dash z dash, they were obtained by translation. There was no rotation involved, that is x axis was translated parallel to itself to the new position x dash axis, y axis was translated without rotation to y dash axis, and so on and so forth. Now in many problems we are required to rotate the axis, no translation, but about the same origin, keeping the origin same, the orientation of the coordinate axis has to be changed. I will give you a very simple example. As you will learn about in dynamics, the moment of inertia plays an important role in the rotation of solid bodies, and that is moment or torque causing the rotation of the body, and that depends upon the moment of inertia about the axis about which the rotation is taking place. For example, there is, consider a rectangular plate which is rotating about its diagonal axis AA, that is axis passing through the opposite corners of the plate. Now, it means I have to find out the moment of inertia about this axis. This may not be easily available in your handbooks or in your tables. So, what you have to do is that you take the value of the moment of inertia about the axis parallel to the sides, that is x axis and y axis, and of course z axis is perpendicular to the plane of the plate. And then I want to transform these values of moment of inertia about to a new coordinate system. At least one of axis of the new coordinate system is along AA, the other can be perpendicular to this. So, it means that I rotate the coordinate system about z axis through an angle, let us say theta. Okay. Then I will, x axis will be the new coordinate x dash axis, which is coinciding with the AA. So, it means under rotation we want to get an expression connecting the new moments of inertia with the old moments of inertia. So, let us do this. So, as I said, in many applications this is needed, and we will now start with the, you could have, you may recall at this point that we did the similar exercise in the case of second moment of areas and the product of areas. That is, if you are given a surface of a given area, then the second moments were converted about one given x set of coordinates were changed over to the second moments and products of area about the new coordinate system. So, it was a coordinate transformation. So, similarly we could have done it for the moments of inertia. The procedure is exactly on same lines, but here I have chosen a slightly different route. Here we will use the correspondence between the moments of inertia and the second moments of area. In our previous lecture, that is lecture 12, we had set up a correspondence between the two sets of quantities through rho t, that is the mass density into thickness of a plate in case the plate is of uniform thickness and homogeneous material. Then the correspondence is very direct. So, here is let us say a body, a plate like body, thin plate, and for this the coordinate system is x, y, z. The new rotated coordinate system, the rotation is through an angle alpha about z axis. So, the new coordinate system will become x dash, y dash, z dash. Now, if I consider any small element of the body here, then its coordinates in the x, y, z coordinates are x and y. In the new coordinate system, it is x dash, y dash. Okay. Sorry, this will be only up to this point. So, this is not needed. This is not needed. This is only up to this point, about up to the x dash axis. Okay. So, we can now project these x dash and y dash onto the x axis and y axis and set up a trigonometric relation and substitute, but that procedure we used for the area moment, the second moments of area. Now, here we are using the correspondence. Well, it was proved earlier in, let us say, lecture 12 that the second moment of area, that is I x dash a, is equal to, that is in the new coordinate, old coordinate system is related to that in the new coordinate system. Okay? And where alpha is the angle between x and x dash axis. So, in view of the correspondence setup there, we can conclude that similar result is obtainable for the moments of inertia, that is I x dash moment of inertia, okay, mass moment of inertia is equal to the corresponding term for the area I x x a cosine square alpha, I y y this is a and sin alpha minus sin square alpha minus 2 I x y a sin alpha cosine alpha. And if you use trigonometric identities, then we can convert this square alpha cosine square alpha, sin square alpha, etc. into corresponding expression for cosine 2 alpha, and then for the mass moments of inertia in the old new coordinate system, I x dash is related to the corresponding terms of the mass moment of inertia in the old coordinate system, I x x plus I y y by 2. Here is the difference, I x x minus I y y by 2 cosine 2 alpha minus the product of inertia, mass product of inertia I x y sin 2 alpha. Similarly, for the other two moments of inertia, that is I y dash m, and these are the expression. And again, using the correspondence, we can have for the product of inertia terms. All right. So, it means we can go back from one coordinate system to another, go to another coordinate system, whether there is translation or rotation, by appropriate formulas. Now, let us ask ourselves a question: in what coordinate system or in what direction the moment of inertia can be maximum or minimum? That is, what is that direction which will give me the maximum mass moment of inertia along that direction, okay, or minimum. So, in other words, we want to find out those directions which will give us stationary values. You may recall it from calculus, differential calculus, that is to find out the stationary value of a function. The derivatives of with respect to the variable have to be set equal to 0. So, similarly over here, to find out the directions along which the moments of inertia will be stationary, we will differentiate the expression with respect to alpha and set it equal to 0. So, the expression for I x dash when differentiated with respect to alpha, that is the angle of rotation, and set it equal to 0, that condition will yield to us the maximum or the minimum values of moment of inertia. Okay? That is, we will get first of all the alpha corresponding to maximum or minimum. So, if I take the expression and differentiate with respect to alpha, either here or here, whichever way you want to proceed, it is immaterial. So, and set it equal to 0 and then simplify. Well, this expression when set it equal to 0 is given over here, and when I take it on the opposite side and divide, we will get tangent to alpha is equal to minus 2 times the product of inertia I x y divided by I x x minus I y y. This is for the 2-dimensional case, plate like body. Okay. If for a 3-dimensional case, the procedure is quite different, quite complex, and we have not considered because it leads to the eigenvalue problem and so on and so forth. So, but for 2-dimensional bodies, this procedure is quite simple. Okay. So, once we have this expression, and suppose I x y, I x x and I y y are given to us, that means right hand side can be obtained, and then I take the arc tan and I will get 2 alpha and hence alpha. So, this is exactly what is being done. Now, this will lead to two values. For example, if the expression is the right hand side is positive, tangent of an angle is positive in the first and the third quadrant. If it is negative, then it is negative in the second and the fourth quadrant of the plane. So, I will get two values satisfying that equation for tangent to alpha, and these two values or these two roots of the equation, they will be separated by pi by 2, 90 degrees. 2 alpha will be separated by 180 degrees, first and the third quadrant or second and the fourth quadrant are apart from each other by 180 degrees. So, it means alpha 2 will be equal to alpha 1 plus minus 90 degrees or pi by 2. And once you have obtained alpha 1 and alpha 2, you substitute back into the expression, this expression or this expression, you will get the corresponding values, which will be one of them, two values will be obtained for I x dash x dash. One of them will be the highest possible value, the other will be the lowest possible value. Okay. So, these are the eigen values of the moment of inertia. Right. And these values of inertia are called the principal inertia, and the corresponding directions or axes along which these happen to be maximum or minimum are called the principal axes or principal directions of inertia. So, for a two-dimensional body, that is a plate-like body with uniform thickness, we can always obtain two directions called the principal axis of inertia. About one direction the value is maximum, about the other direction the value is minimum, and these are so called the extreme values or stationary values of inertia, and these play a very important role in the in dynamics. Now, suppose a body has Ixy 0, then what happens? The numerator is 0, it means alpha is 0 and or 90 degrees. That is, the two axes, x axis and y axis, are themselves the principal directions. So, whenever you have the product of inertia of a plate 0, if you find that a given plate has a 0 product of inertia, then the coordinate axes themselves are the principal axis of inertia. You do not have to do any further calculation, and along the two axes, along one axis the inertia will be maximum and along the other axis it will be minimum. For example, a plate is circular, then you take any two perpendicular diameters, they can serve as x axis and y axis, because along that the product of inertia Ixy will be 0. So, it means any two diameters will be principal axis of inertia, and fortunately maximum and minimum value will be identical. So, because Ixx in this case will be equal to I by y, about any other diameter also it will be same. I have already stated, once you have the principal axis, then the product of inertia terms will be 0. So, your inertia tensor will be equal to inertia matrix is I1, I2. The diagonal terms are the principal inertia and the off diagonals are 0. For three-dimensional case, you can generalize it. Of course, the direct proof is as I said more complicated. In case of a three-dimensional body, in general there will be three principal axes of inertia, and one of the inertia values along one of the axes will be highest, about the other it will be lowest, minimum, and the intermediate about the third axis it will be intermediate between the two. And these three directions are always orthogonal. There is a standard, these are standard results from the eigenvalue problem, but we are not discussing them in detail. Let us take up one or two examples to illustrate whatever we have learned today. I am restricting them to thin plate problems. A thin plate weighing 100 Newton has the mass moments of inertia, they are given about the mass center. O is the mass center, Ixx is 15 kilogram meter square. Sorry, it should have been should not be shifted. It is kilogram meter square. Iyy is 12 kilogram meter square. Ixy is minus 10. See, the mass moments of inertia are always positive, but product of inertia can be positive, negative, or 0. So here it is minus 10 kilogram meter square. What are the moments of inertia about the new coordinate system x dash, y dash, z dash, whose origin is at P, whose position vector as seen from the OXYZ coordinate system is 0.5 I, 0.2 J, 0.6 K meters. Okay. So, the three coordinates of P are known to us. Well, it is a direct use of the parallel axis theorem. So, Ix dash x dash is equal to, in the new coordinate system, is equal to the corresponding moment of inertia in the old coordinate system plus total mass into dx square. The distance between the x coordinates, old and new, the normal distance between the two squared is the normal distance between these two. Similarly, for product of inertias, we have this formula. So, rest is just substitution. 15 is the Ix dash Ixx, okay, and then mass is you have 100 Newton is the weight. So, divided by G 9.81, you will get mass in kilograms. So, you will then the distance between the two axes, normal distance between the two axes, that will be by Pythagoras theorem, the z coordinate square plus y coordinate square, okay, of the point P. So, this is exactly we have done 100 by G 0.2 square plus 0.6 square. So, this comes out to be 19.077 kilogram meter square. Iyy exactly on the same line, the distance between the two, normal distance between the two y axes is 0.5 square plus 0.6 square under root. So, you square it up, and for the product of inertia, again in new coordinate system, old coordinate system, plus mass times xc xp yp, okay, coordinate x coordinate of p y times the y coordinate of p, and this will come out to be minus 8.98198 kilogram meter square. So, that was fairly elementary problem. Let us go to a very more interesting problem now. Here is an inverted T, okay, which is being used as a pendulum, which consists of two thin rods, one rod vertical, the other rod is horizontal. Both the rods are having dimensions 0.6 meter and 0.6 meter. Thickness is much smaller than the other dimension. So, each of them, each vertical and of these limbs of the T section, they are weighing 5 kilogram and they are having a mass of 5 kilogram, and the pendulum is suspended from the top point O as shown in the figure. Compute the moment of inertia of the pendulum about an axis passing through the, first of all, point O and point G, that is axis perpendicular to the screen we are talking about. Okay. So, it is this T pendulum is swinging or oscillating about either O or about G. So, we have to find out the corresponding moments of inertia. Well, using the information available in the handbooks, we will neglect the rounding of the corners, we will consider them as rectangular bars. So, moment of inertia of the body OA, that is the vertical part. So, I have to calculate the moment of inertia about the extreme end, an axis passing through the center of the extreme end. So, that is given by 1 by 3 times mass into length square. Okay. 1/3 of ml square, and mass is 5 kilogram and length is 0.6 as I said. So, 5 into 0.6 square divided by 3, that is coming out to be 0.6 kilogram meter square. For rod B, now rod B, first of all we will find it about its own central axis and then we will shift it to O. You understand? We have this axis which is a moment of inertia of a rectangular bar about its middle axis, can be again obtained very easily from the handbook, and then is shifted from here to here. So, you will have 1 by 12 ml square plus md square once again. So, about this axis passing through the middle, it will be ml square by 12, and then in a parallel manner it is shifted to over here. So, the distance between these two is 0.6 meters. So, we will have md square. So, mass divided by 12 into 0.6 square plus mass into 0.6 square. So, 1.95 kilogram meter square. So, the total moment of inertia about the point O, the top point, is sum of these two expressions. This is coming out to be 2.55 kilogram meter square. All right. Now, to find out about the center of mass G, first we have to locate the center of mass, and for that centroid of the cross section has to be found out. Yc is equal to the first moment of the two masses, that is the vertical part and the horizontal part, divided by the total mass. So, that you can easily see, both the parts are 5 kilogram each. So, 5 into 0.3, well, the center of mass of this vertical part is at half the depth, 0.3, total depth is 0.6. Center of mass is of the horizontal part is at total depth 0.6. So, we have 5 into 0.3 plus 5 into 0.6 divided by the total mass 10. So, the location of G is 0.45 meters from the top. Okay. And then, since we know the moment of inertia about an axis perpendicular to the screen passing through O, the top point, and we have to find it about the center of mass. So, again use parallel axis theorem instead of doing it from initial formulas. You can use the parallel axis theorem at this stage, and Yc is known, the distance between the axis along the y axis is known. So, a simple calculation will give me this Ig as 0.525 kilogram meter square. So, this exercise has repeated use of parallel axis theorem. Let us have one more final example and then we will close this chapter. Here is a plate, a thin plate, which is a quadrant of a circle. various dimensions are given, and the one coordinate system x, y, z is passing through the mid plane of the plate, alright. And now this coordinate system is rotated through an angle 30 degrees about z axis. So, the new coordinates are x dash, y dash and z dash are coinciding. So, this is the middle plane over here. So, you can see that this is how the location of the coordinate plane x y is, or x dash y dash is. Okay, sorry, first let me read the problem. A thin plate having a shape of a quadrant of a circle is shown, and this has the following inertia matrix components. Ix is given, Iyy is given, both will be, because of symmetry, equal 0.1019 grams meter square, and Ixy is given as 0.0649 gram meter square. The axes are rotated through 30 degrees anticlockwise, as we have seen, normal to about an axis, normal to the quadrant. Find the components of the inertia matrix for the reference frame x dash, y dash, z dash. X dash, y dash lie in the mid plane of the plate. So, I have already explained the problem. So, let us go to the calculations. Well, we have to directly use up the formulas which we have derived for the rotation from the correspondence principle of the second moments of areas. So, Ix dash x dash for the moment of inertia is Ixx plus Iyy, that is coordinates, the moments of inertia values in the old coordinate system, plus the difference between the two divided by 2 cosine 2 alpha. Alpha is 30 degrees, so cosine of 60 degrees minus the product of inertia times sine 2 alpha, that is sine of 60 degrees. Rest is substitution. Because both of them are equal, Ixx and Iyy are equal, and this is divided by 2. So, it will be, first term will be 0.1019, second term because of equality is 0. So, and the third term will be minus Ixy is 0.0649 into sine of 60 under root 3 by 2, 0.866. So, I have got it. Iy dash y dash, again using the formulas, okay, we will have 0.1569, and then the polar moment of inertia, that is Iz dash z dash, which is sum of, you remember for thin plate we have already proved, sum of Ixx and Iyy. So, if I add these two, I will get the polar moment of inertia, which is Iz dash z dash. So, 0.2038 grams meter square, and finally, the product of inertia in that plane. Well, again Ixx and Iyy are both being equal. So, the difference between the two is 0, and so the first term is 0, second term Ixy was already given to you, 0.0649 into cosine of 60 degree, which is half, that is 0.5. So, this is what we have got. Finally, all the components of the matrix. So, if I put it in the matrix form, Ixx, Iyy, Izz, these are the Ixy terms. Now, Ixz and Iyz, because plate is of uniform thickness, so the xy plane, because it is lying in the mid thickness. So, you can say the plate is symmetric about the xy plane, and hence Ixz and Iyz are 0. This is what we have earlier stated due to symmetry. So, it means these two terms, and by symmetry these two terms also, they will be 0. So, we have got the complete matrix of the inertia terms for this problem, for this quadrant of a circle. Okay. So, I think now we can close or sum up the whole chapter of moment of inertia, the product of inertia, and earlier the second moment of area and product of area. We have seen how the shift of the axis parallel to the older axis brings in the changes in the moments of inertia terms, etc., product of inertia terms, second moment of area, etc. How the rotation affects and what are the principal axes of area or principal axis of inertia, principal directions, etc., etc. And then also, for if the body is a thin plate, we have a direct correspondence between the moment of inertia terms and the second moment of areas, and similarly product of inertia terms and this product of areas. So, these concepts will be very useful in the dynamics of bodies, as well as later courses in solid mechanics, when you are analyzing beams of different shapes and cross sections. Thank you very much for your attention. In our next lecture, we will be starting with virtual work and energy methods of analyzing equilibrium.